Hey everyone, we're about to start our next session. Again, some amazing content we're going to get through. Just a quick couple reminders. This is a hybrid event, so as you see, we are all here in person, but we also have audiences joining us virtually. So if you want to join in the Q&A in the chat, just go ahead and just scan those QR codes to the left and right of y'all. But if you also want to talk with some of our experts, we do have experiences up on level 5. We get to get some be able to talk to our experts and also get your hands on some cool demos upstairs. So with that, let's go ahead and let's get started.
Thanks. Morning, everybody. How's build going so far? So that's good. Good build. All right. Welcome to Inside Microsoft AI Innovation. My name is Mark Russinovich. Just out of curiosity, how many people have seen a previous version of this particular session? So a few of you have. So you're going to see some new things, those people that have seen this before. And for those of you that haven't seen this before, I hope to show you a highlighted tour through our AI stack from the bottom to the top, focusing on infrastructure. So you've heard a lot about Copilot and writing apps and how to mitigate security risks I've talked about, how to develop copilots on top of semantic kernel. This is going to actually go one layer beneath that to show you how we run AI inside of Azure. And I'm going to start by going through different aspects of our infrastructure, starting with compute. Then I'll talk a little bit about our network and how we design our network, what makes it unique. And then I'll talk about storage and some of the innovations that we've got in storage that we've deployed to make our infrastructure more efficient. And efficiency is the key to the game. And if you take a look at what's happening to challenge the ability for us to be efficient, you can see that the sizes of these frontier models have continued to grow, basically exponentially. The biggest models are the most powerful models, and this trend line doesn't seem to be slowing down. You heard Kevin Scott talk about with Sam Altman that we don't see an end to the scaling law of capability in sight. And what this is doing is driving more and more compute requirements out of the infrastructure. One of the ways to look at this is this amount of compute requires to train these models, because they're not only getting big, but the amount of data that they need to process during a training run continues to grow. So you've heard about tokens, and when you train one of these models, you're talking about not just trillion tokens, but tens of trillions of tokens are passed through the model for them to learn how to get these capabilities. The first AI supercomputer we built back in 2019 for OpenAI was used to train GPT-3. And the size of that infrastructure, if we'd submitted it to the top 500 supercomputer benchmark, would have been in the top 5 supercomputers in the world, on premises or in the cloud, but the largest in the cloud. In November, we talked about the next generation, the 2 generations later supercomputer. So that we built one to train GPT-4 after the GPT-3 one. And this one we're building out to train the next generation of OpenAI's models. This one with a slice of that infrastructure, just a piece of that supercomputer that we were bringing online. We actually did an official top 500 run, and it came in number 3 largest supercomputer in the world, and the number 1 largest supercomputer in the public cloud. Again, that's a tiny fraction of the supercomputer that we're ultimately finished building for OpenAI. And we're already on to the next one and designing for the next one after that, which are multiple times even bigger than this one. Now, to just give you an idea of why they need to scale, if you take a look at the training requirements for something like 𝗦𝗲𝘲𝗀 70 billion, which is kind of a medium-sized model at this point. It's not the largest type model. In fact, Meta is coming out with a 400 billion parameter version of llama-3 in the near future. They talk about that this required 6.4 million GPU hours on an H100, which is the current generation supercomputer infrastructure. If you trained this model on 1 GPU, that would take 730 years to train that model. But on the supercomputer that you see on the left, the tiny slice of it, that would take about 27 days. And again, that's a tiny fraction, so just divide by the multiplier on top of the size of the supercomputer to see that you can start to get down into training a model like this literally in days on the supercomputers we're building. Now, another way to look at the amount of compute required for these models is to look at the amount of memory they require. Because talking about the number of flops or tops that they require for processing tokens, you need to look at how much memory footprint they require. And this is especially important when it comes to inference, loading the model and serving it. If you take a look at inference, you typically load a model in 16-bit format, so 2 bytes. So each parameter is 2 bytes, which means that if you've got 1 billion parameters, that's about 2 gigabytes of memory that you require to load and store that. And so if you take a look at a 175 billion parameter model, which was GPT-3 size, that's 350 gigabytes just to load the model. But that's not all you need for inference. Because you load the model, those are the parameters or the weights, into the GPU. You also have to store the processing of the tokens. And this is called the key value cache, storing what it processed when it's looking at the prompt and starting to generate tokens. And that needs to be retained for efficiency. This is kind of the rough layout of a 13 billion parameter model on a 40 gigabyte A100 GPU. The fact is that the models, of course, are getting bigger and bigger. This is a 13 billion parameter model. If you take it 70 or 400 billion or up into the trillion parameter models that you're seeing at the frontier, then you're talking about many times larger than the sizes of the high bandwidth memory that is coming in these GPUs. So if you take a look at the evolution of GPUs, one of the key aspects of it is not just the performance, but how much high bandwidth memory comes with it. In fact, this has become a limiting factor for GPUs. You can see here, they've been roughly doubling every year and a half or so, up until just this past year, when we saw the A100 80 gigabyte come out, and then H100 came out at 80 gigabyte. Immediately, AMD turned around with the MI300X, which you heard about us launching, at 192 gigabytes. And this made it very compelling for these large models. Not just large models, but loading for inference, as you'll see later. And so this has kind of created a race to build more and more high bandwidth memory. You can see Grace Blackwell 200 coming in at 384 gigabytes of high bandwidth memory. And that makes it extremely powerful for training and especially for inference, because you can load these big models or multiple big models on the same GPU and get more efficiency out of it. So this is one of the reasons why we have this diverse array of hardware in our data centers. We've got the lines from NVIDIA. We've partnered closely with them, driving requirements into them, including information about how to run these large models and why we need so much memory. AMD, so that large HBM that they've got, it's directly through feedback from us and OpenAI. And then our own Azure 𝗦𝗲𝗀100, which you've heard about, our own custom silicon, which isn't a GPU, it's custom accelerator for AI. And that HBM that is continuing to grow, the performance that's continuing to grow, the die sizes that are continuing to grow, is leading to more and more power consumption at the same time. If you take a look now at another dimension of GPU evolution, number of watts per GPU, you can see that this is also growing exponentially because of those other factors. The latest NVIDIA GB200, with all its high bandwidth memory and all its transistors, it's over 200 billion on a wafer, is 1.2 kilowatts just for one GPU. And there's 8 of them in a single server. And that's just the GPUs, not the RAM and the CPUs that go with that. So now you're talking about close to 10 kilowatts of power for just one server, which is just an amazing amount of power for a server in a data center. Now, how do you cool something like this? Traditionally, it's been air-cooled, but we've had liquid cooling for a long time. In fact, this is my home desktop machine, which is liquid-cooled, so that I can play games like Battlefield 2142, which is my favorite game. And this is what it looks like when I run it at 80% GPU utilization, which is when I'm running Battlefield at high res, 56 degrees Celsius. And it's able to run that hot because of the liquid cooling, because there's no way fans would be able to keep it operating at 80% with this. Now, this is the operating temperature for a consumer GPU. The operating temperature for a data center GPU, and by the way, this is a dolly image of our data center, if we don't have a good cooling solution, is you can see the H100 operating temperature top 30 degrees Celsius. So even way lower than what I've got on my consumer GPU. So we've got to force a ton of air. You can see how much air is required to flow through that thing. This is just becoming unsustainable. We cannot push enough air through our data centers to cool these kinds of systems when they get to this kind of scale and to get the density that we need in the data center footprint. So we're having to turn to other solutions, and 𝗦𝗽𝗲 is our first step towards the new design of data centers in the cloud. 𝗦𝗽𝗲 is a liquid-cooled system. This is a 𝗦𝗽𝗲 board. So 𝗦𝗽𝗲 boards have 4 𝗦𝗽𝗲 accelerators. You can see those sheaths there at the top. They're covering the 𝗦𝗽𝗲 accelerator parts underneath them because those sheaths are what carries the liquid into the plates that are on top of the 𝗦𝗽𝗲 accelerators. So these are liquid-cooled systems, custom designed by us. Here's another look at that. This is the liquid cooling in and out that goes into those sheaths, carrying the liquid into those plates. And this is allowing us to keep these systems cool and to save water and to save energy. So it's like a win-win-win. It's more complicated because we're having to design cold plates custom for these things and design custom liquid cooling systems. We can't go buy these things off the shelf. So we've been building custom liquid-cooled sidekicks, and you've probably seen this video before of the 𝗦𝗽𝗲 rack, which consists of 2 sides. This is on the right, the back of the 𝗦𝗽 accelerator. There's 4 𝗦𝗽 servers on the top, 4 𝗦𝗽 servers on the bottom, the front-end networking in the middle, and then that second cabinet next to it is the closed-loop liquid cooling system. You can see the liquid cooling that was there on the back, those giant cables carrying liquid, hot and cold, into and out of, or cold and hot, into and out of the 𝗦𝗽 rack next to it, and those cables that we just saw on the slide before it. This is actually, like I said, our first deployments of liquid cooling in the Azure data center, and it is the trend. You will see liquid cooling for next generations of GPUs coming out from AMD and NVIDIA for their high-end offerings into the data centers. And we're prepared for this both with a sidekick like this that will work with those systems, as well as liquid-cooled natively data center footprints that can support liquid cooling without the sidekicks. The sidekicks let us take this liquid cooling into any data center. Now, power, when we look at the power consumption of these models, we see something interesting. For training, once you get a training run going, you get up to close to 100% power draw and stay pretty constant there as the training run goes. There might be a few dips and spikes, but inference is a little bit different. And we'll take a closer look later. But with inference, you can see these very spikes. Low power, relatively low power, and then a big spike. What's happening there are the differences between prompt processing and token generation, which I'll get into later with some details. But what we saw when we took a look at these traces in the data center is that we can actually save power by running not at 100% draw, rated for 100% draw, but by oversubscribing the power in the data center. The idea is when you have so many of these jobs happening at the same time, they're not all going to spike at the same time. So there's going to be an average power utilization, which is below that 100%. And you can see the kind of headroom that we calculate. 3% for training, 21% for inference. That means we can oversubscribe power by 20% safely. So we're building systems and actually started to deploy these in our data centers that are monitoring the power draw of these GPUs and servers, and then basically oversubscribing the power and with the ability to cap or throttle when we are reaching limits. If they all happen to suddenly spike at the same time, we don't want the data center to fail. So we throttle the frequency on the servers. We also throttle the power going into the racks through software-managed power control in the data center. And what this is doing is allowing us to put 30% more servers in our existing data center footprints. This is literally hundreds of millions of dollars of saving through power every year. And so a lot of questions I get is, what are you doing about sustainability? Lots of things. Liquid cooling is more sustainable. It's actually much less water usage than our air-cooled data centers. And this is another way that we're getting more sustainable, is just by making more efficient use of that same power. Now let's talk about networking. In networking, just to give you an idea of the networking requirements of large-scale AI, an AI training job uses something called data parallel processing, where you've got lots of instances of the model all learning different parts of the data at the same time. And then there's this thing at the end called all reduce, where they all share what they've learned and update together. This sharing requires massive coordination across all the GPUs. They're all sharing information with each other across whatever scale they run at. And if you take a look at the scale of those systems that I was talking about, those AI supercomputers, they're tens of thousands of servers. And they all have to be connected together to make that efficient all reduce happen. So this requires high bandwidth connections between them and low latency. And within the servers, you also need low latency because there's basically like mini data centers inside those servers. There's 8 GPUs on one of those GB200s or H100 systems, or the MI300X, and they're connected through their own custom high-end high bandwidth connections that have 1.2 terabytes, not terabits, terabytes per second of network bandwidth between those GPUs. So if you can stay within the server, you get amazing amounts of network bandwidth. Now, coming out of the network, the servers, we now have 400 gigabit InfiniBand links coming out for each GPU. So there's a total of 3.2 terabits of networking coming out of these servers. And that is all connected through our custom InfiniBand topology. We're the only cloud that has InfiniBand at this kind of scale. And this is really the only difference between the supercomputers we build for OpenAI and what we make available publicly, is the scale of the InfiniBand domain. In the case of OpenAI, the InfiniBand domain covers the entire supercomputer, which is tens of thousands of servers. In the case of our public systems, where we don't have customers that are looking for training at that kind of scale, or even we're not training at that kind of scale, the InfiniBand domains are 1,000 to 2,000 servers in size, which is still 10,000 to 20,000 GPUs, which is a massive supercomputer itself. So you can get a massive supercomputer of that scale in Azure through our public infrastructure. Now, I like to look at pictures of what's inside these things. This is NVIDIA H100 system. You can see the 8 GPUs up there. These are the back of our racks. Those cyan cables, that's the InfiniBand cables. We've laid down at this point enough InfiniBand in our data centers to wrap the Earth 5 times. And by the way, the amount that we're scaling out our systems, Kevin Scott talked about this, or I think Satya did, 30x since November. We've built out 30x the size of our AI infrastructure since November. The equivalent of 5 of those supercomputers I showed you every single month, and that rate continues to increase. So this means we need to lay a lot of cabling, both for our front end and back end networkings. Now, not all the innovation has to be super high tech. One of the 3 ways that we've found is the traditional cabling in data centers was very low tech. It required technicians to just go along, pulling the cables, stretching them between servers, and just hugely inefficient. So what our data center incubations team came up with is 3D printed what they call boats with something called Jeffries that allow them to take these boats and pull them down sleds that are above the racks to pull that cabling. And this saves them 3 times the time it takes to lay down the cabling. And we're using this on our front end networks to lay down that much cabling. We started with InfiniBand, but we've now got a different solution for InfiniBand. But we're using this now in all of our data centers, starting to build this out. So not really a super high tech. These are 3D printed things, but innovation, comes in whatever way innovation comes. Now let me talk a little bit about storage. So training, especially models and videos, are big, like we've said. You need to distribute them to all these servers. For inference, the same thing. Lots of models deployed on these clusters. How do you distribute all of that data, the models, the model checkpoints, the key value caches if you need to move them or reload hot. What we've built is, inside of our infrastructure, custom cluster storage. We call it Storage Accelerator. The idea here is we want to make this extremely simple and extremely reliable. You don't need really a parallel file system for this. You just need something that can pull data in, distribute it within the cluster so it doesn't have to go all the way back to storage. And so the solution is when a worker needs a model, for example, it goes and checks if it's got it, or if the cache has it. If it doesn't, it pulls it in, and then it distributes it to the other servers in the cache, which are typically the cluster, the GPU cluster that's assigned to this particular inference domain, for example. And it distributes this through either InfiniBand or Ethernet, depending on the cluster. And it does it without interfering with the running workloads there. So it can take advantage of all the free bandwidth to distribute these things around so that another worker, when it needs something, can very quickly get it from the cache, even over InfiniBand. So parallel reads from the cache, these are stored in blocks. There's no metadata server. There's no replication across the servers. It's very simple and very fast. And I'll show you a quick demo of that right here. So on the left side is without the storage cache. We're going to load in 𝗦𝗲𝗀𝗶𝗶𝗀𝗲, again, coming directly from Azure Storage. On the right side, it's going to pull it from another cache node over InfiniBand in the cluster. And what we'll see that it took about 12 minutes to load that from Azure Storage. This is 270 gigabytes of data. And it took less than half that time to pull it from the other server, the cache in the cluster. This is really important for the model as a service that we've announced, because we're going to have lots of models in these clusters. We need to very efficiently get the models up and running on whatever GPUs that get assigned to. And this is just a fundamental physics problem. How do you get that data loaded? So that's a look at the kind of hardware and the lowest layers of the software for running our AI infrastructure. I'm going to go one level up and talk about how we resource manage all of those GPUs in that infrastructure. And important to keep in mind that what we're aimed at with all of this is efficiency. Power efficiency, time efficiency, making a use of those resources as close to 100% as possible, so we're not wasting anything. And to support that, we've got micro optimizations and we've got macro optimizations. Let's start with the macro optimizations. Everything that I'm talking about now is built on something, our internal AI workload platform. It's a resource manager that knows about an AI job. It also knows about AI models for inference, and it's called Project Forge. Internally, it's got a different name that we decided wasn't. Internally, it's called Singularity, which kind of has some negative aspects to it. So I'm not supposed to tell you that. But you can see that it's got a bunch of subsystems associated with it supporting these things. One of the key ones is this global scheduler. So this global scheduler treats all of the GPUs and all of the regions around the world as a single pool, and we call it one pool. And the idea is that when we have that kind of capacity to resource manage, that we can do it more efficiently. Because the challenge that you have with looking at cluster by clusters is something that we had at Microsoft up until last year, and that we see many enterprises have, which is you assign GPUs to individual teams. And this has two problems. One team doesn't use all their GPUs, and those GPUs they're not using are sitting there doing nothing. Another team has used all their GPUs and would like to use more GPUs, but they don't have access to them, including the ones that the next team next to them is not using. So the idea with one pool is everybody gets a virtual GPU, not physical GPUs. They get a certain amount at a certain priority. We've got 3 priority levels: low, standard, and premium. And if a premium job comes in and there's a low priority job running on the GPUs it needs, low priority gets evicted. Now, the interesting thing about the eviction is that this is a global pool. And just because it gets evicted from a cluster in a particular region doesn't mean there's not capacity somewhere else that it can use. And Project Forge knows that. So it might say, well, you need A100s. This higher priority job needs your A100s. You get evicted. You're going to go now to another region, and I'll restart you there on those GPUs that the higher priority job can't use. And if you take a look, we've migrated all of our first-party training onto one pool. And now, if you take a look at 3 different teams here, this is actual charts from 3 different teams' utilization. You can see Team A has over 100% utilization. And the reason why it's over 100 is because that's their guaranteed capacity, but they were able to use more because these other teams aren't using all their capacity. And so this is the benefits, and the average total overutilization now across these 3 teams, if you just take a look at them, is about 100%. And if you take a look in aggregate across all of Microsoft, for all of our GPU usage for training, we went from 50 to 60% utilization to between 80 and 90 right now. And we expect to get even higher. And so this is all benefits to our bottom line and costs that we pass on. Now, another benefit of Project Forge is the reliability system. When you're running these large jobs, they take days, weeks, or even months in the case of some of those frontier models. And you're inevitably, with that amount of hardware, going to have failures on a pretty regular basis. We see failures on those large-scale systems. If you have 1,000 GPUs, you're going to see a failure roughly every 2 or 3 days of some kind. A GPU is going to fail, a server is going to fail, RAM is going to fail, a network link is going to fail. And if you're having to babysit those jobs and manually restart them, manually diagnose what's going on, manually move it to another healthy server, you're just never going to make progress, and you're going to have horrible utilization and efficiency. So Project Forge is designed with reliability in mind. This is an actual trace from Project Forge dashboard. It's got automatic failure detection, so it'll automatically detect if any of these kinds of parts fail. It'll automatically diagnose it. It'll automatically take it out of rotation, automatically file tickets for the support, data center support people. And it will automatically restart the job again from the checkpoint on healthy servers to let it continue. This is the way we get basically automated, long-running reliability for our jobs. This is, by the way, actual trace. This is, for example, some of the Phi 3 runs that were done on Project Forge. Like I said, all of our runs, including all the Phi runs, happen on top of this Project Forge infrastructure. This is 1,024 GPUs, a job that ran for 2 days, 11 hours, so close to 2.5 days on 1,000 H100 GPUs. So let me take a look at micro-optimizations now. If we take a look at the anatomy of an LLM inference, it's broken up into 2 phases. The first phase is called the prompt phase. This is where the whole prompt is processed in parallel. This is the really efficient phase because the GPU can do the whole thing at once. Boom, using all of the compute on the GPU, and it gets the prediction for the next token, which in this case is yes. Now it goes back and it's entering now the token phase or the generation phase or the decode phase. People call it different things. And at this point, it's doing next word prediction one at a time. This next word was yes. What's the next word? It is, and then that's it. S. End of sequence, EOS. So this is the token generation phase. Now, very different characteristics from these 2, which we'll get into in a second. But also, different AI applications have different ratios of prompt versus token generation or decode. On the top left, content creation, short prompt, long generation. On the bottom right, long prompt for summarization, short generation. And then you can see chatbots and enterprise chatbots are kind of in the middle. If you take a look at naively scheduling prompt and generations on the same GPUs, what's going to happen is this. You get a prompt come in from one session. The GPU starts to process it. And another prompt comes in while it's generating, and that first generation slows down because the GPU now is busy dealing with that second prompt. Now that second prompt, when it's finished, it goes into generation mode, and now you're into memory constrained rather than GPU constrained, GPU processing constrained. But now they can both proceed without interfering with each other. So the problem is these prompts that arrive and just demand a lot of GPU that interfere with the existing generations that are happening. How do you deal with that? Well, we developed an internal project called Flywheel to deal with this. How many people have heard of PTUM, or PTU Managed offering? So a few of you have. This is our serverless GPU offering for inference. And it works on top of Project Flywheel. The idea is we don't want to have to give you a whole GPU for your inference, where now you're responsible for getting that thing to 100% utilization. We'd like to give you a fraction of a GPU. And we're going to share that GPU with other customers, of course, in a very secure way. We're not mixing prompts and tokens from different customers. But we need to do it in a way that gives you guaranteed performance, because you don't want your noisy neighbor. Like you're doing, your app is running, and suddenly another prompt from another customer comes in, and now your app slows down. So Project Flywheel is aimed at providing that enterprise-grade consistency. So a prompt comes in, starts generating tokens, normal speed, and another prompt comes in. We don't process the whole prompt, we chunk it. And we interleave its prompt generation with the generation of the tokens from the first prompt. And now you don't get any that kind of interference effect. And the key here is how do you do that and provide a consistent delivery of throughput, which is the way that you want to measure. What's the throughput of my generations? So I want to show you a quick demo here of Project Flywheel. Up at the top, this is actual trace from Project Forge, Project Flywheel. You can see naive prompt and token processing. Some of those big blocks are the big prompts coming in. The small blocks are the token generations for different sessions and different colors. You can see that they're all over the place, and you big gaps of white. Those whites are wasted GPU. Plus, the latency, the throughput, is all over the place for these different sessions. Now, on the bottom with Project Flywheel, you can see everything's nice and consistent. All of the blocks are the same size, whether they're prompt or generation. Now, here's 3 different workloads. One that has big prompts and small generations, one that has about a balance, and then on the right, small prompts, big generations, to demonstrate different AI workloads. They all have different throughput requirements, and we're going to run them and then plot what throughput Project Flywheel is giving them, because they've each signed up for their own throughputs that they need for their app to behave well. And you can see they're all in different colors. You can see prompt tokens per minute. You can see the different green, yellow, and blue for those different mixes. And you can see generated tokens per minute. So the blue obviously is generating a lot of tokens. That's one that would be doing the generation, the kind of small prompt, big generation. But you can see all of them have very consistent throughput, very consistent latency, because of that multiplexing Project Flywheel is doing. Another way to benefit of this is you can dynamically raise the throughput on any one of these, and it will, if there's enough capacity on those GPUs, go up. So this is the way that you can dynamically, without having to go buy another GPU, be able to get a slice of GPU and be able to dial up and down how much of the GPU you need as your job changes, your application changes require. So that's an example of a micro-optimization. I want to show you another one. How many people have heard of LoRA, or low-rank adaptive fine-tuning? So a few of you have. This LoRA is the way that people fine-tune AI models now. Now, let me talk about what fine-tuning is. Fine-tuning is when you take a base model and you want to give it new data to train on to change its behavior or to give it some new knowledge. It's typically change behavior, like I want you to speak in JSON format, or I want you to speak like a doctor. That would be an examples of fine-tuning. The way that traditionally it was done is you make a whole copy of the model. You basically continue the training by giving it small target data set, like examples of doctor talking. And then you spit out a new model that knows how to talk like a doctor. This is really inefficient. So we came up with a way to make fine-tuning much more efficient by training what's called an adapter. So you create some extra weights called an adapter instead of copying the whole model. Then you train the whole thing, but you don't modify the base model, just this adapter weights. And what you end up with is a fine-tuned model that is really the combination of the adapter plus the base model. So you can have literally thousands of fine-tuned versions of the base model. Each one of those adapters is small. How small? Well, if you take a look at a 175 gigabyte, or 175 billion parameter model like GPT-3, you might have an adapter size of just 100 megabytes. And so to train, fine-tune traditionally, 96 GPUs, 24 GPUs for LoRa. 1 terabyte per 100 model weights for traditional fine-tuning, 1 terabyte base, plus 200 megabytes for LoRa. And then switching between models takes minutes to load that big giant model with a new version that is fine-tuned. For LoRa adapters, you just need to load the adapter. And then it has no downsides, really. No additional inference latency. You get more training throughput at the same time. So this is LoRa, and this was developed by Microsoft Research. And it is the industry standard now for how to do this. But we've taken it one step further inside of our production systems, because if you take a look at, we've gotten this fine-tuning as a service now with GPT-3.5, now we have GPT-4, and we have other models coming, fine-tuning as a service, where you just give us a data set, we take care of the fine-tuning. You load your fine-tuned models. There's going to be lots of different fine-tuned adapters on top of these base models. We don't want to just be able to load one, remove it, load another one. And if you take a look at traditional fine-tuning, that's what you're doing. But if you take a look at something we've developed called multi-LoRA fine-tuning, which we've got deployed, we load multiple LoRa adapters on top of the base models. And then they're all in the GPU, so when a request from one customer comes in for the doctor adapter, it gets processed. When another one comes in for the lawyer adapter, it gets processed at the same time. We don't have to load and unload. So I got a quick demo of that. So here, I'm going to do traditional inference with one LoRa adapter loaded into the model without multi-LoRa. You can see when I try to load a second adapter and query it, I get a failure because the model's not ready, because it's trying to load the new adapter and hasn't finished by the time I sent the request in. So I'm going to load 100 models into the second GPU, or sorry, 1,000 models into the second GPU. And I'm going to just ping a few of those LoRa adapters, and you can see that I'm getting responses from all of them because they're all sitting there in the GPU. And so this would be the equivalent of multiple customers coming in with requests at the same time for their different fine-tuned models, and we're able to serve them all because of this efficiency. And the question is, does that impact the performance of those serving? Do they interfere with each other, these LoRa adapters? You can see on the left is a single GPT-3.5 fine-tuned adapter. On the right are 1,000 of them being queried all at the same time, and the latency is the same. So no performance degradation, no impact. But we're able to serve 1,000 models, basically. It's basically, think of it as 1,000 custom versions of GPT-3.5 on the same GPU. And this is the 10 model concurrency latency run for 10 models, 25, calling them 25 requests at the same time. So this is another really key way for us to raise the efficiency of those GPUs in the world where we're going to have lots of fine-tuned models out there. So another example of kind of the innovation that we've got. Now I want to switch gears and talk about the evolution of computing in general. So when we take a look at cybersecurity, it's been a world of logical protection of data. You've got encryption at rest, and this is something that all the cloud providers now have, both server-side keys, where we're encrypting the data, and then customer-managed keys, where you can define your own keys and encrypt the data a second time on top of that. You also have encryption of data in transit. All network communications expected to be encrypted now. And that protects the data in transit and at rest, but what's been missing is protecting the data while it's being used. It gets to the server, either loaded from storage or through the network, and now it's in the clear when it's decrypted, and now it's being processed as part of a training job, part of a data analytics job. It's sitting out there in the open. And what's it susceptible when it's sitting out to, what kind of risks when it's out in there in the open on the server? Well, it's susceptible to somebody that breaches the infrastructure. It's susceptible to insiders. It's susceptible to operators that get access, administrators. What we want to do is keep that data as secure as possible through its own life cycle. So something called trusted computing emerged in the late 2000s with ARM Trust Zone and Intel SGX. And I got in, when I went into Azure and I was looking at SGX, realized that this would be filling in the third leg of this data protection coverage, protecting data while it's in use. Now, what are these technologies? They're originally called trusted execution environments. We've branded it as confidential computing, this concept of protecting data with hardware. And that hardware protection is based on a root of trust in the CPU where it creates effectively a box, an encrypted box in the CPU's memory. Nothing can get into it after it's been created. Nothing can see into it after it's been created. And it's even encrypted physically when that data leaves the CPU and goes to memory. So even somebody with physical access can't easily sniff the memory bus, for example, and see the data. So you get logical protection and physical protection. But it's not just that. The real key to confidential computing, besides just that inherent protection, is being able to prove that you're protected. So that workload running inside of that box can ask the CPU, give me proof that I can present to somebody else that I am this code, I'm this piece of code, and I'm being protected by you. And this is called an attestation report. And that attestation report can be handed to another application. It can be handed to a human with a policy evaluation on top of it. It can be handed to a key release service set with a policy that says only release this key if the code is this and it's being protected by this hardware. And this then creates this sealed environment, this confidential computing environment, where the data can be processed with and minimize the risks of those other kinds of attacks that I talked about. Since the early 2010s, we've been working with Intel and AMD to bring out confidential computing hardware that can not just support what are called enclaves or small boxes, but actually full virtual machines. And a couple years ago, we announced with AMD the first confidential virtual machines, and we released them in Azure. And then we've announced confidential virtual machines with Intel, their TDX technology, and we've released them in Azure. But the time for confidential computing is really coming because we've been working for the last few years with NVIDIA to co-design confidential computing with them into their GPU lines. And the first line to have confidential computing in GPUs is the H100. The H100 has this trusted execution environment on it, which protects the model weights, protects the data going into the model, encrypting them, and being able to attest to what's inside of the GPU. So that, for example, you got this confidential virtual machine on the left, it's talking to the confidential GPU, and now it can release keys to the GPU to decrypt the model or to decrypt a prompt, and then re-encrypt the response going back to an end user. This actually is fleshing out now the introduction of confidential accelerators with confidential GPUs for AI confidentiality. And this has got me really excited because there's a bunch of scenarios that are just very obviously going to benefit from this. One of them is protecting the model weights. And you might want to protect the model weights because there's a ton of your IP in the model weights. So you don't want them to leak. And confidential computing can provide another layer of protection around them. But more generally, when it comes to AI, the data that AI models process is extremely sensitive in some cases. And what this allows is you to protect that data end to end for things like fine-tuning. The data that you're going to fine-tune the model on can be protected and given only to the GPU. The data that you give as your prompt and the response you get back can be protected with confidential computing. I'll give you one example that's got everybody very excited is confidential speech translation and speech transcription. Speech is incredibly sensitive for a lot of enterprises. And with this, you'll be able to send encrypted speech into the GPU, get a transcription back that's encrypted, and nothing can see it from the point that you send it in to the point you get it back out, other than the GPU. And then finally, a really exciting scenario is confidential multi-party sharing. Different parties get together and share their data, but without each of them being able to see the other's data, because they're sharing it really with the AI model and the GPU, not with each other. So I want to show you a really quick demo that kind of shows you a nuts and bolts view of confidential retrieval augmented generation. So I think all of you know what retrieval augmented generation is. It's when you give a model some information that it wasn't trained on into its context so it can answer questions about it. And the idea here is that the RAG data can be very sensitive. So I'm going to show you this. Here's a website that uses confidential computing attestation to decide whether it trusts the site. And you can see that the attestation information for this RAG website here, this is a website that we're connecting to. That was its attestation from the GPU and the CPU. I'm deciding I trust it. I can examine the attestation report, see that it's got the right versions of the hardware that I like, the right versions of the firmware. And then I can decide to create a policy that is, I trust this policy. And now when I query the attestation of that website according to that policy, I get a green. And I can look and see this thing conforms to the policies I set, so I trust it with my data. Now, if I ask this model, what is confidential computing? This model doesn't know about confidential computing, unfortunately. And it's going to say, I don't know what it is. But now this is a confidential RAG app running on a container on a confidential virtual machine with a confidential GPU. I can upload my very sensitive information. In this case, it's confidential computing documentation. That goes into a vector database, which is sitting in the confidential virtual machine, same with embeddings there. And now I can ask it, what is confidential computing? And it knows. The whole thing was protected from my client side on the browser all the way into the GPU and back, including the data, the document that I uploaded, protected. So nothing outside of that hardware boundary could see it. And so this, I mean, I think I see some nods. You can see just how powerful this is when we bring it to scale at providing just another level, a massive jump in the level of data protection that we can achieve. And by the way, this is just showing if I tweak the version that's in my policy, now I get, hey, the website doesn't conform to the policy you specified because it's got the wrong version of a particular piece of firmware. So I know now, oh, I don't trust this thing anymore. It's not the versions that I trust. Now I want to conclude that kind of gives you an overview of some of the innovation we've got going on in Azure. And you're going to see confidential services coming. You're going to see more innovation in data center efficiency, in serving efficiency, and hardware efficiency. The innovations that we'll have drawing with our next generation, the 𝗦𝗲𝗀 accelerators. I want to just transition and give you a little look at some of the research that I'm doing as a conclusion, because I'm having a lot of fun with AI myself. And this is my own research, which is getting my hands dirty with AI, Python, PyTorch, our own systems like Project Forge, so that I have really a good understanding of the technology underneath and the way that we deliver our technology through things like Visual Studio Code and Copilot, because I've been using Copilot a lot. So one of the things that I did with another researcher in Microsoft Research that works on the Phi team is look at the question, can we have a model forget things? Now, let me set this up with, why would you want a model to forget something? When you talk about these training jobs, even a few days on 1,000 H100s is a huge amount of money. And certainly if you're talking about jobs that are even bigger or running longer, that's a tremendous amount of money you're spending on training one job. What happens if you find out that you trained on data that is problematic? It can be problematic because it's got PII on it. You're leaking private information that you didn't realize was in the training data. What happens if it's got copyrighted data that you are unlicensed to train on? What happens if it's got poison data that's gotten into your training set and is causing the model to misbehave. Do you want to go retrain from scratch? It would be nice if you could just have the model forget those things. And so that's what we set out to do. Now, it turns out, we said, what can we have a model forget that really shows, gives us a challenge, and really people can see that it really forgot something? What do AI LLMs know? They all know what topics have they know so clearly that it's obvious that they really deeply know them. Well, that's going to depend on how much of the data they've seen as they train. So we thought about it for a while, and then we realized one of the things that all these models seem to know is the world of Harry Potter. They know Harry Potter because there's so much Harry Potter. The Harry Potter books are all over the web, it turns out. And so these models that are just scraping the web suck in a whole bunch of copies of Harry Potter into their training data. They see so many copies of it that they almost memorize, if not memorize, Harry Potter. So we're like, if we could get these models to forget Harry Potter, that would be really cool. And so we set out to do that, and we succeeded. And so this is a research paper you can find in arXiv that we wrote, Who's Harry Potter? I want to show you a quick demo of our Who's Harry Potter model and how it works. So on the left side, you can see 𝗦𝗲𝗀𝗀𝗶𝗁𝗏. And you can see when Harry went back to class, he saw that his best friends, what do you think it's going to say? All we said is Harry and class. And it says to see Ron and Hermione. Think about that for a second. Harry in school, Harry Potter. Like there's no other Harry in the world. So they really, really know and like to talk about Harry Potter. So here's the unlearned one. And it says, instead, saw his friends Sarah and Emily. And it's very consistent, too, with that generation. So this was the key. How do we make it forget, but yet be very natural and not degrade its performance otherwise? So that's unlearning. And now the second thing we're working on is how can we take it and forget it particular topics, like particular words or particular concepts? So we're continuing down this line of research. And the latest thing we are doing is, for example, showing how we can make it forget words, like profanity. So this is the Mistral model, which it's not ashamed to swear. It's a warning. And we're going to ask it, write a rant about inflation filled with profanity. And we blurred this. Yeah. But you can see that it's like, sure, here you go. And then we say, what are the top 5 most profane words in the English language? OK, so I don't know which those words are. Now, here's the forget version. So we want to, again, make it very natural. Like, how do you make it not talk about profanity but sound natural? Here's a rant. The same prompt. And this is actually using the model itself to figure out what it should say instead, is the key to this research. And then here's the top most profane words. And by the way, the first one we didn't put in the dictionary, so we were like, that word is, yeah, not that bad. All right, but you can see, you get the idea. Anyway, so I've been having a lot of fun. And I can tell you, let me just sum it up by one thing. Copilot has been indispensable. I'm an expert with Python and PyTorch. I can do stuff so fast with Python and PyTorch because of Copilot. My brain is really lazy. So if you took Copilot away, I'm like a Python noob still. Like, have me do a list comprehension, and I'm looking at the documentation if I don't have Copilot. But I've gotten so to the point where I just have AI generate all of that kind of code for me. I have it give me advice on how to optimize code. So this has been a huge boon to my productivity. I'm doing this kind of stuff as a side projects that if I didn't have Copilot, I just would not have the bandwidth to do. That said, if you're a software developer, you have nothing to fear, at least for the near future. Because these models, while they're great at that, kind of help and autocomplete, and here's a short little function. For more complicated, nuanced tasks, they just aren't there yet. And so there's been many rounds where there's bugs, and even flagrant things like, you just wrote me a function where you use a variable you didn't define. It's, oh, I'm sorry, here's the revised version. All right, you still didn't define it. So we're still at that kind of level, but that's, like I said, I just can't live without it. It is so powerful, and they're just going to get better. So I just want to leave you on that note on use of AI for programming. And with that, want to wrap it up, and hope you found this an interesting tour of some of the innovations we got going, from hardware to data center design, to the way that we manage the infrastructure on micro and macro optimizations, to the future of confidential computing, and then a look at some of the kind of fun research that you can still do kind of on the side with just a single server of GPUs. So this is kind of a really fun time to be working on innovation at any level of the stack. So with that, hope you have a great build. Hope you have a great party tonight. Hope to see you next year.